So for number 3, so these particles are there. Electrostatic force F in the charge, 2 others, the magnitude, blah, blah, blah. Determine the signs of the charges Q1 and Q2 indicate the correct signs below. So if there is a net charge, this right here, this thing is positive. So if there's a net that way, then I'm guessing this needs to be negative and this needs to be positive. Yes? And the reason I say that is this negative would do this, positive would do that, and they could result in that as an answer. If I did this as a positive, then it would be pushing that way. And then the resultant of those two would be up there somewhere. So the red is if I had chosen to make Q1 positive, it would flip, that vector would be up here, and I'd get some result like that. So in order to make the net force go to the left, I have to make sure that they work out. And then I can't just randomly pick stuff because this magnitude is bigger than this one. So this arrow right here is probably going to be bigger than that. Okay, so then that means I would say Q1 is negative and Q2 is positive. See, because I know, even if I don't know anything else, how can I follow these lines? Right? I have to follow those 2 lines and get 2 vectors that add up to be this. So it has to be those 2 vectors. See what I just did there? It has to be this plus that. So then I just move that over there. Those are the 2. There's no other way to do that. Because the 2 have to end up, and they have to follow the lines. All right, on the diagram below, label arrows indicate the directions of force F1. Observe the product 1, 3. Oh, so okay, so they're saying put the 2 things there. So remember, I have to follow the triangles, bidding, if you will, and then using kind of like the parallelogram method, I can see the size. So like this, and we could say this is like F1, this is F2. Now, notice it says label, so you have to put the names. If you don't, then okay, calculate the magnitude F, the electrostatic force on particle 3. Yeah, so it's just get the numbers. Okay, so for part C, if I want to calculate F, then F is going to be equal to these 2 vectors here being added up. So I just have to add them up. And it's going to be equal, the components of F1 put on F2. Then F is going to equal the square root of F1 squared plus F2 squared. Of course, the only reason I can say that right off the bat is because why? Yeah, because this is a 3, 4, 5 right triangle. Right? If that wasn't a right angle, then I can't immediately use, I can't use pythagorean. I have to use the log cosines on all sides. I have to use a bunch of junk. I need to crack a bunch of vectors. Okay, that's fine too. So for F1, I'm going to say K. And then Q1 is 4 times 10 to the minus 6 times Q2, which is 1 times 10 to the minus 6, over 4 meters squared. And then F2 is going to be K 1.7 times 10 to the minus 6 times 1 times 10 to the minus 6, all over 3 meters squared. So then I just add those, I figure those out, plug them in here, and get some answer. Okay, this is 4 times 10 to the minus 12, over 16, so that becomes like, whatever, basically just divide by 4 down here, 1 times 10 to the minus 12 by 4. That times 9 would be 9 times 10 to the minus 3, divided by 4, which would be 3 point something. 16, yeah, so or something like that? No, 2.25. It's like 2.25 times 10 to the 3. No, minus 2. Yeah. Minus 2 newtons. Over here, this one's ugly. So actually, square this. That becomes, actually, this isn't ugly. Square this, that becomes 9. That gets rid of that. So then it's 1 times 10 to the 9 times 1.7 times 10 to the minus 12. So the answer is going to be 1.7 times 10 to the minus 3. Right? So get those two things, plug them in, get our answer. Questions? Just to keep us on the straight and narrow here, let's take a look. Q1's name positive, that's good. Bing, bing, there's our 2. And bada boom, bada bing, bada bang. Good, we're good. Alright, calculate magnitude of electric field position part 3 due to 2 particles. Alright, same smell, right? We can do the same thing where we're saying E1 and E2. So this is a minus, this is a plus. Here it's going to be like this, here it's going to be like that. Right? Now, the question is, what is the difference between E and F? Yeah, it's Q, right? So this is going to be K. This is going to be Q. Is this called 1? Q1? Yeah. It's going to be KQ1 over that R, which is 4 meters squared. This one's going to be KQ2 over 3 meters squared. So you're going to do the same thing. Get those two things, and then say that this is going to be E. So E total is going to be the square root of E1 squared plus E2. All right, and Mr. Branch just stole my thunder, but it's okay. You can do all this. No, that's good. You can do all this stuff, or as Thomas said, well, hey, wait a minute. Don't we know that E is F? Sorry, it's FQ. F over here. Good, great. F is E is F over Q. So that means if I just take the force, which we calculated, right? The force total here, and if I just divide it by this Q right there, okay, notice it's got to be that one. Then I'll get my E. And the E's in the same direction. What's that? Oh yeah, that makes life easy, right? You're right. I think that was 1 times 10 to the minus 6. Cool. That makes life easy. Alright, so we're good there. Yeah, so we can switch and take a look, see if that's, yeah, there you go. Just take E is after Q. Life is good. Now, on the figure below, draw a small X in the box in a position where another positively charged particle could be fixed in place so that the electrostatic force on particle is 0. So, obviously, if I want to put a positive, if there is a net, yeah, electrostatic force. There's a net force this way, so that's F total right now. And I want to get rid of it, right? And this is a plus charge. What do I have to do? And what's that? Yeah, it's going to be this one, right? Oops, put a plus, which means it will not be directions. X in the box where a positively charged particle could be placed. Now, where could you put another particle that would also work? Yeah, you could put a negative over here, right? And that would work just the same. But the key is it's a positive. Then how would I justify that? I would say that this would be whatever F mu, right? And then I could put a charge there. That's appropriate amount to cancel out. Yeah, lights repel. So going back to here, yeah, correct position, justification refers to forces, all right.